Morning, guys. Just a couple of bookkeeping things. Your test or no class on Friday. Though you have a reading assignment due on Friday, and you have a homework assignment due next week that I just put up. That'll be the last assignment that you'll have before the test, which is a week from Friday. We'll have a help session on that Thursday at 3 o'clock. Excuse me, not 3 o'clock, 4 o'clock. And I will send you an email about that. I think 4 o'clock. Just wait for my email. After this, after we're going to it. And with our help sessions, just like last semester, we'll do the extra credit. So if you come to the help session, that's great. But try to come in soon. I think sort of right before the test to cover all that material. What's that? No, not this Thursday. Next Thursday. We'll try to have them more regularly. Just haven't seen you here. Don't have time right now. I'm sorry. Don't have time for you. But okay. That's selfish. All right. Do a help session for goodness sake. All right. Just want to give you a little perspective of what we're doing. So on this next test, you're going to see lots of different things sort of rumbling around. We're going to see forces, right? Our Coulomb's law, KQQ over R squared. You're going to see 2D forces like we did. You'll see some conceptual questions. You'll see some with 2 charges and some with 3 charges maybe, where you're finding the net force. We'll also see electric field. Remember we had 2 definitions for electric field. That's this E equals KQ over R squared. Again, 2D forces. And then also the force due to an electric field, F is equal to QE. That's based on our definition of the electric field. So we'll see those things, and those sort of look similar. But then we're also going to see potential, which we'll call V, which is KQ over R. And we're going to see that today or on, what's today, Wednesday, or is it Monday? Wednesday? We'll see it today or next Monday. You'll see it in your reading too, where you find the potential due to a point charge. So this is potential. This is sometimes called a voltage, although in this chapter we'll just call it potential. And then we're also going to see potential energy. I'll use a PE for this. And this is going to be our KQQ over R. That's the energy that's contained within two or more charges. If I have 2 charges, they have a certain amount of potential energy. Because if something has potential energy, it has the potential for what? When we talk about an object, if I lift it in the Earth's gravitational field, I say it has potential energy. It has the potential for what? For what? It has had work acted upon it to give it this potential energy, but it has the potential to do what? To move. It has the potential for motion. When I do work on an object, I give it energy, and I hold it, and then if I let it go, it moves. Well, if I have 2 charges, they have potential too. They have potential energy. Because if I let them go, they're either going to fly together or they're going to fly apart. It all goes back to these forces by Coulomb's law, that those give it this potential for motion. And so we're going to see this as well, potential energy. And those are the big topics for the test. Those are the only topics for the test, in fact. But of course, we'll see some calculations and we'll see some conceptual stuff. But I just want to lay it all out for you as we move into potential, because potential and potential energy, students often get those sort of all jumbled up with electric fields and electric forces. Partly just because, they look a lot the same. KQQ over R squared, KQ over R squared, KQ over, and then sort of all those K's and Q's start rumbling around in your head. Unfortunately, you have the equation sheet, so that will help you to keep those things straight, but I find it helpful just to see them laid out like this as we move forward. Okay? You look really excited to study potential today. Okay, so let's see. So potential difference and electric potential. You'll see this in the reading and in the homework, which is due, I think I made it due on Tuesday, the homework assignment. I just posted. Do y'all know? Have y'all seen it already? I just posted it. You've seen it? Really? You just checked it. Okay, yeah. All right. Those are good test questions. Okay, so as you're going through the homework, especially my new students, y'all know this, right? Courtney and Emily, you know this, right? That I will pull questions from those homework assignments for the test. Not the personalized questions, because everybody's are different on the personalized, but from those questions that everybody has. Okay, so electric forces are conservative, just like gravitational forces. We saw conservative forces last time. What types of, not last time, last semester. What types of forces are conservative forces? Forces that don't require what? Contact, right. So contact forces are not conservative. Forces that are field forces are conservative. When we say that they're conservative, it means that they conserve, well, what do they conserve? They conserve energy. They don't lose energy. They don't lose, or you can think, conserve energy. Contact forces, whenever you make contact with something, that loses energy in the form of friction and thermal energy and sound and a variety of different ways that you lose energy. A conservative force is path independent. Remember, when we were talking about forces, we sort of used the idea of a mountain, and we said, well, you can take two different paths up this mountain. You can go from here up to here, or you can go from here and follow switchbacks all the way to the top. And the amount of work that's done by the forces that are involved will depend sometimes on the path and sometimes not on the path. Conservative forces are path independent. So the work done by conservative forces is path independent. That means that the amount of work that our gravitational force that it doesn't matter if I go from here to here or if I follow the switchback trail all the way. It doesn't matter. It's path independent. That the gravitational force will still do the same amount of work. Conservative forces are path independent. And so electric field forces are also path independent. It doesn't matter as I move two charges together, whether I move them straight together like this or if I follow some circuitous path. It doesn't matter. All that matters is my beginning point and my ending point. And that's true here. The beginning point and the ending point are all that matters for conservative forces. All right, so let me fill in this. Conservative forces are field forces. Really, as far as we're concerned, we only know of two field forces, gravity and electric forces. And then non-conservative forces, these are contact forces. The work done by non-conservative forces, is it path independent or path dependent? Path dependent. So non-conservative forces include friction, going back to our mountain analogy. The non-conservative forces include, like your feet rustling along on the ground. It depends which path you take up. You'll expend more work going up the circuitous path. It's a longer path, and so your frictional forces are expended over a longer distance. Whereas going up this path, even though it's harder for less time and for a shorter distance. And so you expend less work going straight up the side of the mountain than taking the switchback trail. Okay, so we saw this also last time, the work energy theorem, last time meaning last semester, that if I do work on an object, I change its energy. Sometimes that'll be potential energy. Usually we think of it in terms of kinetic energy, though, and we'll sort of think of it in terms of that here when we're talking about the work done by electric forces. That when an electric force does work on an object, on a charged object, then it will change its kinetic energy. You'll see some homework questions on the assignment for OpenStax that are similar to this, where if I do work on an object, on an electric charge, it increases its speed. Just to remind you, kinetic energy is 1/2 mv squared. That's not on your equation sheet, but it'll come up on the test. And you'll see some questions, we'll work some, but you'll see some on the OpenStax as well, where you have to use that idea. If work causes an increase in kinetic energy, then what happens to the potential energy? Well, if I have a system that has a set amount of energy, and I increase my kinetic energy, what's going to happen to the potential energy? Is it going to increase, stay the same, or decrease? Right, it's going to decrease because I have a set amount of energy, and if I change one, then the other is going to act in response, the opposite. Because I have this much energy. If I add some, or if I increase one side, I have to decrease the other side. So the potential energy, if the work causes an increase, will decrease. So the potential energy then is equal to the negative of the work. And this applies only when an electric field is constant. Don't worry, we'll apply some of these things and you'll see why they're relevant in just a bit. All right, so let's think about this. These are two metal plates, transducers, like that guy in the TED Talk. These are transducers. They're just metal plates, and they have an electrical energy applied to it, a voltage, a potential. And I put a charge in between these two metal plates, like you did in lab. So this is our positively charged side. This is our negatively charged side. My electric field lines run from the positive side to the negative side. Because I imagine if I have a positive charge here, it will be repelled from this side and attracted to this side. So the electric force is to the right. And so my electric field is also to the right. Again, you can think of these as having all positive charges on one side, negative charges on the other side. I imagine my positive test charge, it feels a force that is repulsive from the positive side, attractive to the negative side, and so the electric field is from left to right. This is also a capacitor, and we'll begin to see these in the second part of this chapter, but you will not have capacitors on the exam. So if you're working, or as you're working through the old exam, when you get to capacitors, you're not going to see that on the exam coming up. Most of the time on exam 1, we don't get the capacitors, so most of the time it's not an issue for you, but if you do, occasionally, we'll get that far. So if you see capacitors on the exam, is it on the exam? No, not on the exam, no capacitors. All right, so consider a particle that moves from A to B. Has the electric field done positive or has it done negative work on this object? If it moves from left to right. Now remember, work is equal to force times displacement. Well, we talked about work, how you have last semester, where if my force and my displacement are in the same direction, is that positive or negative work? It's positive if they're in the same direction. I'm increasing the energy of the object. But if the force and the displacement are in opposite directions, positive or negative work? Negative work. So in this case, as this object is moving from left to right, is it doing positive or negative work on this positive charge? It's doing positive work because the force is to the right and the displacement is also to the right. So this electric field is acting upon this positive charge and causing it to move from this position over to this position. Force and displacement in the same direction. So positive work. Has the potential energy, then, of the object increased or decreased? Has the potential energy of this object increased or decreased? It's decreased because, let's see, I only have a set amount of energy, right? My kinetic energy has gone up, so my potential energy goes down. So since kinetic energy has gone up, my potential energy has gone down. Or I can think of it as the work is equal to the negative potential energy. Our potential energy is equal to the negative of the work. I think that's how I wrote it earlier. Let's write it that way. Negative of the work is equal to the potential energy. So if positive work has been done on the charge and potential energy is decreased, what type of energy does the charge now have? I wrote it up there. But what type of energy does it have? It has kinetic, thank you. So it has kinetic energy that this charge now has. It now has kinetic energy. So the charge has lost potential energy at point B. Its kinetic energy must have increased. Or look, it would be NCRSD. See, you know what that means, right? Increased. Yeah. All right, then we can calculate the charge's speed at B. At point B, rather. And remember, our kinetic energy is equal to 1/2 mv squared. And this kinetic energy will be equal to the work that's been done. By the way, I can calculate this work. I think I write this, but let's just go ahead and show it here. Since I know that work is F times D, then I know that my force is equal to Q times E, right? That's our definition of our electric field, or based on our definition, that's our force. And then I just multiply times D. In this case, it'll be X, because it's moving in the X direction. So the work is equal to the charge times the electric field times X. Pretty sure that's on your equation sheet, but that's all it is. It's just saying work is force times displacement. This is our force. This is our displacement. That gives us the work that's been done on the charge by the electric field. Just like gravitational fields, nothing different here, except when we were talking about gravitational fields, it wasn't QEX, it was MGH. But it's the exact same construct, right? Where I'm talking about the force, mg, or QE in this case, times the distance, or the displacement of the object. Okay, let's do an example. And again, like I said, you have some problems like this on the OpenStax, and I certainly see some on the test too. All right, so I have this proton. It's released at some point, -2 centimeters, in an electric field of 1,000 newtons per coulomb, and I want to know its velocity at 8 centimeters. So I want to know the change in kinetic energy. This is going to be equal to the work, which is equal to F times D, which is Q times E, times X. So if I want to know the change in kinetic energy, it's going to be the charge. Remember, for a proton, the charge is equal to 1.6 times 10 to the minus 19 coulombs. So it's 1.6 times the electric field, which is 1,000 newtons per coulomb. And notice my coulombs cancel, and that just leaves me with a force in newtons, as it should. And then my distance, well, I'm going from -2 centimeters to 8 centimeters. Oh, gosh, what is it? Is that 6 centimeters? What is that distance? It's not 6. 8 minus 2 is 6. What is it? It's 10, right. So it's 8 minus -2. Because I'm moving from -2, I go straight past 0 and then all the way to 8. So it gives me a total displacement of 10 centimeters, but we want to have that in SI units. Remember, I take my decimal place 2 places over, and so it's 0.1 meters. So times 0.1 meters, and that's equal to, well, 1.6 times 10 to the minus 17, I guess. That's in joules. That's not our answer, though. Really, I want to know what is the velocity. But this energy right here is equal to 1/2 mv squared. So I say 1.6 times 10 to the minus 17 equals 1/2 mv squared, and I solve that for v. Now recognize that when I'm dealing with a proton, students sometimes get confused by this on the test, by the way, so just beware that if I tell you it's a proton or an electron, boom, you already know 2 things about it. You know its mass and you know its charge. Okay? You might not know those numbers right off the top of your head, but they're on your equation sheet. They're in the upper left-hand corner. I got the fundamental unit of charge, that's the charge of a proton and an electron, and then I have the mass of the proton and the electron. But they're just good numbers to have sort of on the tip of your tongue, and you'll use it in chemistry too. I think. I'll use that in chemistry? The charge of an electron? Proton? Yeah. All right, so the mass of a proton, let's see, that's the big one. So it's 1.67 times 10 to the minus 27 kilograms. Once I do that, take this and plug it in for M, then I solve for V, and V is equal to 1.4 times 10 to the 5th meters per second. Just another reminder, people, because I've seen several people come to my office, and when you're using your calculator, I've said this before, when you're doing scientific notation, it's a lot better if you use the EQ button than using the times 10 to the whatever. One, it just doesn't take as much time, but it also helps out with your order of operations. So I really encourage you to use not the times 10 to the whatever, but the EQ button. It will save you some heartache in the future. If you want to know how to do that, just drop by and see me. I'll show you. Okay. You with me so far? Is this exciting? No? It's kind of exciting because we're building up to being able to use charges within circuits. I mean, when we have electricity flow through an electrical device like this or whatever, all that we're doing is we're setting up an electric field and we're moving electrons from one point to another. And when we move them from one point to another, we give them energy. And then that energy comes out in the form of, heat, or light, or music, or whatever. Okay? So that's what we're moving towards, is we'll be able to use these ideas in an electrical circuit. Okay, so the electric potential difference between 2 points A and B is the energy per charge that's gained as the charge moves from point A to B. You have a question on your OpenStax bit that asks just what is potential? And the answer is something like energy per charge. Potential, not potential energy, potential and potential energy, those are two different things. They're related, but potential is an energy per unit charge, energy per charge. So when it moves from one point to another, say it's moving from point A to point B, have a charge that moves from point A to point B, it changes its potential. So it has a certain potential at point B, and it has a certain potential at point A. At this point, it has a certain energy per charge, and at this point, it has an energy per charge. And the potential difference is just the difference between those two values. If these are the same, then it has a potential difference of 0. There is no change in energy per charge. But if these are different, then it can either have a positive or a negative change in potential, a negative or positive potential difference. The units here are a volt. We abbreviate this with a capital V because it's named after Voltaire. And these are the same basic SI units as a joule per coulomb. Or that would also be, what's a joule? It's kilogram meter squared per second squared per coulomb. Right, joule is mv squared, so kilogram meter squared per second squared over coulomb. I might give you some questions, just what are the basic SI units as we begin to build these things. I did that some last semester. Or did I? Did I give y'all questions about basic SI units? I did, okay. You might see that again. So just beware sort of what the units are. So since the change in potential energy is equal to the negative of the work, which is equal to negative QE times delta X. We've already seen that before, right? The negative, because if PE goes up, or if KE goes up, PE goes down. That's where that negative comes from. This is our force, this is our distance, F times distance gives us work. And then that causes a change in potential energy. So since that's true, and I define my change in potential as a change in energy per charge, then I can also define this as negative EX. Let's just leave off the X, actually. Negative EX times delta x. This is just a little derivation, but I'm getting to something here, but I just want to show you where this comes from. All I did here is I just took this and I divided it by q, and then I'm just left with this E delta x. That's all I did there. Just got rid of the q. Because this is our definition of potential difference. It's my change in potential energy between two different points divided by the charge. And then Ex then is negative delta V over delta X. All right, so this gives us the more typical unit. I showed this to y'all some days ago, but a Newton per Coulomb is what we've been using for electric field, but don't be surprised if you see on the test either Newtons per Coulomb or you see volts per meter. All right, so that gives us sort of the more typical unit for electric fields. All right, so let's think about how charges move in a potential. Actually, let's see. Yeah, let's do a few clicker questions. All right, proton and electron are in a constant electric field. We release the proton from the positive side and the electron from the negative side. Which feels the larger electric force? They're in this constant electric field, meaning it doesn't change, it's always the same. Notice the lines are always equally dense, so the electric field doesn't change. Which feels the larger electric force? Feel free to share with your neighbor, okay? Ask your neighbor what they put. You know, sort of all over the board. But more have it right than wrong. So let's stop at 120. 120. All right, peeps. Listen, the answer is E because, well, my force is charge times electric field. The electric field is the same for both the proton and the electron, right? The electric field is what it is. And the proton and the electron, which has the bigger charge of the proton and electron? They're the same, right? I mean, they're opposite of one another. And so the proton and electron, they're going to feel the same magnitude of force, but the opposite direction. The electron will feel a force that is to the left, and the proton feels a force that's to the right, along with the electric field. We stated that, but let me just make sure that's clear. Electrons always feel forces that are opposite the electric field. That's sort of the inverse of our rule for finding the direction of the electric field. You put a positive charge there, ask yourself the direction of the force, that's the direction of the electric field. Well, electrons in an electric field will feel a force opposite the electric field. And that's what we see here. Which has the larger acceleration in this electric field, this proton and electron in the electric field? The electron is released from this side, the proton is released from this side, this one goes this way, this one goes that way. Which feels the larger acceleration? All right, let's stop at 45. Okay, good. B is right. The electron Y, it's itty bitty. It's like 1/10,000th the proton's mass. And so it feels the same force, but it gets a much larger acceleration. Which one has more kinetic energy? Ah. Ask your neighbor. Ask your neighbor what they put. You not put anything in? You don't do anything. Don't share your answer. Share your proof. Right? All right, let's stop at 118. 118. Okay, C is right. Listen, the energy is equal to the work that's done by the electric field, and that's equal to the force times the distance. That's equal to Q times E, that's the force, times the distance. Well, let's see. Q is the same for both, E is the same for both, and D is the same for both. So they're both going to have the same kinetic energy. Now, one of them's going to be going faster, right? The electron's going to be going faster, but it also has a much smaller mass. And those two things will counteract one another. And likewise, this one's just going to be trolling along, but it has a much bigger mass. So they both have the same kinetic energy. All right, we'll come back to this. Okay, so let's think about how charges move in a potential. This will help us a little bit as we move along. Positive charges accelerate from, well, let's first talk about when we have this sort of nomenclature. When I have a positive side of these plates and a negative side, I call the positive side the high potential, and I call the negative side the low potential. High potential, low potential. You can think of them as just high potential, low potential. Just remember, the positive is high, the negative is low. And positive charges will move from high to low potential. And that makes sense, because a positive charge will follow the field lines. The force is in the same direction as the field. So it goes from high to low. And then the negative charges move from low to high potential. You want to see a skill that I have? Not many people can do this. I worked a long time on this. And it doesn't have anything to do with it, it's just the words. Low, high, low, high. Can y'all do that? Try it. It's like rubbing your belly and patting your head at the same time. Go ahead. See, you can't do it, can you? Hardly anybody. Of all the students I've ever had, I've had like 2 students that could do low, high. What? You can't think about it. All right, but charges move from high to low potential, and negative charges move from low to high potential. This is kind of nice because you can build a potential in the lab, and you can build it to look like whatever you want. It's not that difficult. It's kind of like playing electric field hockey, that you can build an electric field that looks like whatever you want just by placing charges in certain positions. And so what that allows you to do is to move charges from one place to another, or to isolate charges and keep them in a place and not move around at all. Let's try this one. Consider this graph. This graph shows potential versus X position. So we're just thinking of a charge in line land. You ever read Flatland? I haven't had it. Well, line land is a one-dimensional land, and you can only move in this direction. You ever read that book? It's a great book. You got to read it. It's a mathematical parable. In line land, you can only move in this direction. And so that's what we have here, a charge that can only move in the X direction, but as it moves in the X direction, the voltage changes, the potential changes, the energy per charge. So over here, it's big and negative, it gets pretty close to zero, and it changes, it becomes positive. So I want to know, if I release a positive particle at point A, what's going to happen to the particle? Which way will it move? Will it move to the left, to the right? Will it be stationary, or will it oscillate around point B? What will the particle at A, a positive particle at point A, what will it do? All right, we'll stop at 128. 128. All right, A is right, because positive charges move from high to low. Positive charges move from high to low potential. So this charge is starting at A, it's going to move from high potential to low potential. It'll move in this direction, to the left. Its X position will decrease. What happens if you put a negative particle there? What's going to happen? What will happen to a negative particle if I release it right here? When negative charges move from low to high. So what does that make it do?
We let it go at A.
Yeah, you let it go at A. And what does it do at point A? All right, I'm going to stop at 40. B? No, it's not B. It's D. Woo, woo. Yeah, that's what I'm talking about. B is sort of right, and B is right initially.
It took right to get to B, but then it would go down.
It's not exactly wrong. I'll still give you a joke. How about that?
Yeah.
All right. So if it starts here at point A, it will move from low to high potential, and then it's going to sort of overshoot B a little bit, and then the electron is going to say, oh no, I'm moving from high to low, and it's like it's going to swing back the other way. And so this electron is just going to oscillate back and forth. Hey, can anybody say radio antennas? That's what radio antennas do, right? They set up a potential like that, and that electron, it zooms back and forth. What? And that's what radio antennas do, is they move an electron back and forth, at a particular frequency. But that's how they do it. They set up a potential with a battery, right? Set up a potential on that metal pole, and you can move that electron back and forth, just depending on the potential that you set on. This isn't really a joke, it's just sort of, I don't know, a proverb, if you will, or a worldly wisdom. If you ever get a bladder infection, you're in trouble. Come on. All right. So the negative particle will oscillate around B. Okay, so why is this important? It allows you to isolate charges because we didn't have this in the question, but also if I had a potential well like this, and if I put a positive charges move from high to low potential. And so what's it going to do? If I put a positive charge down in that little hole, nothing. It's going to sit there, right? It's stationary. And likewise, if I put a negative charge right here, it's just going to sit there. It's not going to move at all. And that's like tweezers for an electron, that you can take an electron and just keep it in the same space. Yeah? No, I got that right? Positive charges move from high to low potential. So this one's already at a low potential. It can't go any lower. And negative charges move from low to high potential. It can't go any higher.
But, so the right goes higher. You see what I'm saying? So the right of the proton, it goes down.
Oh, but no, a proton moves from high to low potential.
But the electron.
The electron right here?
It's not going to go to the higher.
Uh-uh.
Okay.
Oh, no.
Okay.
I see what you're saying. I see what you're saying. Like, would the electron go over here? Is that what you're saying?
Yes.
Yeah. So anyway, it allows you to isolate charges, move charges around, like in electric field hockey, or like in a radio antenna. It's just a nice way. Like I said, they're like tweezers for electrons. And that, when you think about it, it's like, how do I move a charge around? That's not easy, right? Because they're not. You can't put your hands on them and move them around. But this is a nice way to do that. Okay, there's those FETs. Y'all did those in lab, so we're not going to do them here. All right, let's look at electric potential and potential energy due to point charges. You'll have a few questions like this on the test, and indeed, you have it on the OpenStax thing too. The potential due to a point charge is given by this, KQ over R. I'm going to get out of here. 10:50? 10:35? The electric potential due to a point charge is KQ over R. That's on your equation sheet. You just need to know how to use it. I do want to point out, though, that when R goes to infinity, when R is really big, that V is equal to 0. That's important later. That if I go really, really far away from a charge, the potential is equal to 0. So if I have a charge here, right here, at a distance R, the potential is, whatever it is. But as I move really far away, if R is really, really big, then V approaches 0. It becomes 0. That if you move far enough away from a charge, basically you just don't see it anymore. It doesn't affect you anymore. I'll show you the derivation, because I know y'all like that. Our potential is E times delta X. Remember, I showed you earlier how E is equal to delta V over delta X. In fact, that's where we get the volts per meter. If you're in the 200 level, actually, we begin to talk about this in terms of partial derivatives. And the electric field you can figure out from the potential, which is kind of useful. But we're not going to do that in this class. So our potential difference is E times delta X. I'm going to rewrite that as E times R. Just make X and R just because. That's KQ over R squared times R, which is KQ over R. So that's our expression for potential, KQ over R. It looks a lot like electric field. It looks a lot like electric force. And it looks a lot like potential energy, which we'll do next. So just be careful as you're mixing and jumbling all those together. The electric potential is y'all ready for it? Because you're going to be happy. Yeah, Haley? It was just sort of doing units. Yes, you're right. It is supposed to be negative. But I was just doing a loose derivation. All right? Y'all ready for it? The electric potential is what would make your day if the electric potential is what type of one? No, that would be bad. Because then you have the tangent and all that. Yeah. The scalar. If you want to think of it as a vector quantity, now you can do so. But it's a scalar quantity. So when I got a bunch of charges, I don't have to deal with vectors. I just add up numbers. It makes life a lot easier. So the potential of multiple charges adds like numbers. You know, 1 plus 2 equals 3, and not like vectors. Which is, you know, like 3 plus 4 equals 5. I mean, that doesn't make any sense, right? But that's how we add up vectors. We're doing the whole triangle thing and all that. Okay? So that'll make our life a lot easier. You'll be appreciative of it when you see those problems on the test. Let me show you something before we do this question. So the voltage, or the potential, is KQ over R. Here, unlike what we did before, we will include the signs. So a positive charge has a positive potential, and a negative charge has a negative potential. So what that does is if I have, say, a plus Q here and a negative Q here, at a point, say, in the middle of these, I have two potentials that are interacting. I have K times plus Q over R, and then I also have K times minus Q over R, and that's equal to 0, because the Q's are equal and they're equidistant between those two objects. If I have two equal charges, but they're opposite signs, and I'm equidistant from both of them, my potential will be 0. It'll cancel out. I have 0 potential at that point. And so that brings us to this question. If I have 4 charges like this, I want to know at point P, what is the electric field? Is it 0 or not 0? And what is the electric potential? Is it 0 or not 0? Now your electric field is going to add up like vectors. The test charge, put it right here, ask yourself the direction of all the forces that are acting on it from those 4 charges. The electric potential is a scalar. You ask yourself, how do these 4 potentials add up? This point is equidistant from all 4. So will it add up to be positive, negative, or 0? Let's try this out. All right, we'll go about 8 more seconds. Stop at 50. Oh, sorry. Okay, so A and C look like the popular answers. So everybody, or most of you said that V is equal to 0. That's true. All I do there is I say, well, the potential due to these two, those are going to cancel out, and these two will cancel out. Do I have the same number of positive and negative charges, all equidistant from this point P? And in this case, I do. So the potential is 0. And then I need to go in and get my positive test charge and figure out what is the field. So due to that charge, the field is in that direction, because a positive charge would feel attracted towards that. Due to this one, it's in that direction. Due to this one, it's in that direction. And then due to this charge, it's in that direction. So the electric field is also 0. The electric field is 0, and the potential is 0. So that's A. All right, let's calculate just as an example, and you'll have to do this on the test. You'll get a collection of charges, 2 or maybe even 3 charges like here, and I'll ask you what is the potential at a particular point in space. And in this case, I have Q1, 2, and 3. They're all 1 meter from a point P, and I just want to know the potential. Well, the potential is going to be the sum of all the individual potentials. That's going to be V1 plus V2 plus V3, which is going to be K Q1 over R plus K Q2 over R. Well, Q is all the same, so I'm just going to do 3 times that value. So it's going to be 3 times 9 times 10 to the 9th. Q is 3 nanocoulombs. Gosh, what is nano? I always forget this one. -9. Divided by the distance is 1 meter, not squared or anything. These cancel, so it's 81 volts. I like that purple. I like the purple, okay. Yeah. I like the blue. I'm a blue guy. I like the blue. Sometimes the red, so it's kind of harsh. All right, you're going to have some questions where you have multiple charges, and you have to find the potential due to those charges. I might have one on the next page, do we? Yeah, like this one. So here, I have 2 charges. Let me show you what I did here. This one is plus 2Q. Q is 2 microcoulombs, so this one is 4 microcoulombs, positive 4 microcoulombs. And then this one's minus 8 microcoulombs. I want to know what is the potential at this point. I'm going to try that on your own. Let's try to wrap up. I know only 6 have rung in, but let's try to do about 10 more seconds, maybe. Let's guess if you're not sure. I'll stop at 210. 210. Oh, looks like most of you have it right. 210. Going away. I ring in. All right, I think A is right. Is that right? Yeah. Look, an easy way to do this is to say, oh, I got 2Q and minus 4Q. They're both at 1 meter. I could just find out the potential for minus 2Q, right? Because that's sort of what's left over after they cancel out. And so if I do that, I'll do it the long way in just a second. But if I do it the easy way, I say that V is equal to K times minus 2Q over R. That's 9 times 10 to the 9th. Times negative 2 times 2 times 10 to the minus 6 divided by 1, and that's equal to 36,000. Is it 36,000? It is 36. Micro is -6. You got that? No, that's right. All right. Anyway, we'll stop there. We're out of time. The long way is to do KQ over R for each one, and then adding them all up. And you get the same thing. Okay? Have a great day. I'll see you on Monday. No class on Friday.